Hello. Good morning, Professor Matson. Uh, this is Lorenzo,
And this is Jonathan.
This is Aaron.
and we are here today to present our tiny file system. Before we start, we'll preface with our apologies for our late submission. Um, At the end of the night, a lot of integration was happening, and it carried on further on than we thought. And because of the size of the features, we really wanted to see them through and come up with a implementation that was at least um, functional and documentation that's readable, rather than turning in something that was rather incomplete at the deadline. So we hope you can give your understanding. But without further ado, let's just get into the demo. Um, so here is our TinyFS demo. I will first demonstrate libdisk real quick. So libdisk does behave as per the spec. We have a big suite of tests for libdisk that you can go through. It's more thorough, but for the sake of presenting all systems and modules, we'll just show you some of the more broader tests. So let's grow this here. So here's what's going on. So we make a disk emulator, and we call open disk. We make it a block large. A block is 56 bytes again. We have this function called libstatus, which will display the status of data structures in our disk library. We have a dictionary here. Then we close the disk, and we get the libstatus again. So after closing the disk, you'll see that it cleared the entry, which was the disk number to the file mapping. So that was working. Now this next test makes sure that when we write something to a disk, it stays in the disk even after closing it. So here's an empty disk. We write some stuff to it. So we wrote a bunch of ones. We closed it. You can see here we ran close disk, then we reopened it again, and the ones are still there. So that is all working. Now I will hand it over to Jonathan for the TinyFS features.
All right, this is Jonathan, and I'm going to be discussing over our file system implementation and some of the decisions we made that are clearly visible in our demo run. So we start our demo by just creating the new file system. We mount it, and then we're going to start out with just a dump of the blank file system. So if we come in here, after we make a new file system and mount it, we can see that we allocated about 6 blocks for this file system. And from the looks of it, we have our magic number in our super block. Our root inode block has the correct magic number, and then the rest of our blocks are marked as free because we don't have any files in this file system yet. Some things to note: we usually designate our first byte of each block for an identifier, so we know what type of block is in here. A 0 for the first byte indicates a free block. The second byte of our super node will point to the block number of our root inode. And you can see that we will be using bitmaps and a lot of offsets to store metadata. So in our super node, our next couple bytes will be used in additional features for some file system metadata. And after that, we'll begin our bitmap of our free block list, where each bit, either being 0 or 1, will indicate if the block is free or not. Going into our root inode, we will begin having a file names appearing once we start adding them, and they will start linking to the rest of our data blocks. So let's get into that. If we open a new file that doesn't exist and dump it again, we can see we added a new file. So we named the new file file1, and we wanted to write to the file with this string showing we can write data. After printing the dump, we can see that file1 now exists in our root inode. Take note of the second byte in our root inode, this will indicate how many files we currently have in our file system. The one being our first file, file 1 being our name taking up 5 more bytes, and you'll notice 3 blank bytes. This is a fixed size in our file system, as every file name will be padded to take up 8 bytes regardless. The ninth byte will indicate the block number of the inode pertaining to this file. So we can see this points to block number 2. If we look at block number 2, we have the identifier for an inode file. We have some metadata information, and after that, we can see it starts to point to our data files. So this data file will begin at block 3. And if we look at block 3, we have an identifier, and here is our data we wrote to this file. One thing to note is this second byte of our inode indicates how many data blocks are associated with this particular file. So going through our testing, we can open up a second file and just printing the status. We can see in our file descriptor table, we contain file descriptors which will link to the block numbers associated with the inodes of each file, just as a way to indicate files that are already open and without going through our root inode to get that information. So if we look at our second file, we wrote more data to it, and we can see, let's start with our supernode. Going past our metadata, we can see that we start having some bits be activated. This indicates that more blocks are being taken up and marked as not free. Going into our root inode, we can see our first files here, our second files here, and we can take note that our second file now begins its inode at block 4. Being over block 2 and 3, block 4 will contain metadata and the position of the first data block in block 4. Again, we can see there's one data block associated, and here is our data. Now, if we want to try closing our first file as we go next in our test suite, we close our first file and print out our file descriptor table, we can see that file is now removed. One thing to note is that being in the file descriptor table is how we indicate files that are open, but these files still exist in our disk and file system. So we can still take a look. They exist. When we reopen the file, as we do in here, we'll go back through our root inode, check these byte maps, and add the file again. One thing to note is the file descriptor has now changed. This is because on every time we open a file, we will just give it a unique file descriptor number. So our next test will test out our read byte function. So we're going to want to read from our first file. This will start from the file pointer. These file descriptor table will also indicate file pointers as the second bit of information tagged in with the file descriptor. So we can see that in file 1, we start we start at 0. So if we read the first byte from file 1, we get back an 87. And this is exactly what we expect because our first byte is a W, an ASCII value of 87. Reading the second byte is a 101, which can be a lowercase e. This shows that our incrementation of our file pointer is working and our reading bytes is working. Now, trying out our seek function, we want to seek to the third byte. This will update our file pointer, and if we read a byte at that point, we can see we get a value of 99. This is expected because in this file, if we seek to the third byte here, we have a C indicated by our 0th bit, first bit, second bit, third bit will be C. So our seek function and writing are both indicating that they work. Now, if we want to try deleting the first file, we can see that it does get removed from our file descriptor table. We now have our second file here. And one thing to note is the data actually still stays in our file system, but by the way of our file system works, we can see that our root inode has been updated and now indicates that only one file exists. We can see that file 2 has now shifted down to compensate for it, so we will never actually look further than this first file's data when we read and write and do all of our logic. So functionally, the file is gone. Going back to some more tests, we want to unmount the file system, printing out the status of our file system class. We can see the disk is now unmounted. The file scriptal table is clear. So if we want to mount this file system again, it is already pre-existing and it can now be mounted. Let's open that file again. We can see that now the disk is mounted. We can see that after opening the first file, it is back here. Indicating that it starts at our third block. Finally, we're going to go to some additional features. We implemented a renaming and root directory printing function. So if we just print all files currently in our file system, this will scan through our root directory inode. We can see file 2 and file 1. Now note that it does find file 2 even though we didn't open it. This is intentional as we want to list all files regardless of them being open or not. If we want to test out our renaming functionality, we can see that we rename file 1 to new file 1. And after printing out the file names again, file 1 has been renamed. Now, our final feature is timestamps for creation, access, and modification times of our files. And if we print out the timestamps, you can see that we get a nice human readable format. Now, this metadata gets updated every time we appropriately access or open these files and is what's actually stored in the inode's metadata. And this is essentially the basic functionality of our file system.
Hello, hello. So we will talk about the encryption feature of our file system. So our file system leverages a TPM, which is a trusted platform module. We made a class for it, which does all the functions of a TPM, like creating the keys, storing the keys, and then accessing the keys. And of course, like modern TPMs, it will use some authentication options like biometric authentication in order to verify it's you before it provides the key. So like our retrieved key like uses our prompt biometric function, which will require biometric authentication. And of course, it will generate an actual TPM module. This is like what's in it right now. It's gibberish, but it's actually all the keys used in our file system used by our file system program for encryption. So now let's just, without further ado, let's get into the demo. So that's going to be basically using our file system with encryption. So the first thing you'll notice is our TPM is prompting for authentication. Let's see what happens if we put something that's invalid. If it gets mad at us and does not allow us to have the key. Now let's do this properly. So the key is my finger. So in this case, I mean, in the real world, this would be like Windows prompting you to put your fingerprint or something. So I give it my finger. It does this a few times because there's a few accesses going on in this program here. And as you see, we have an encrypted file system. You can tell it's encrypted because all these blocks, which are mostly zeros, besides the start of the block, are all gibberish because it is using CBC or chain block cipher. So it is essentially using the previous block to then encrypt the next block, and so on and so forth. Sorry, cipher block chaining. My bad. Um, so that is a good sign. Now let us, so this is what happens when we make the file system. Let us try to now mount it. So that would cause the file system to be decrypted because we need to use it. and voila, we have a bunch of zeros, and we have the original indicators in our blocks. So like this is the INO block. And what's going on next down here um, is we're doing some IO. So we wrote to like the block, so it's still writable. Of course, if you as you may see here, we have a bunch of gibberish, but this is actually the hashed. Um, this is basically a password that is hashed um, with that special key. So this allows us to do password authentication um, with your TPM. So you need those two things in order to unlock or decrypt your disk. So um, it's pretty neat. Now let's proceed. Oops, it's not valid. So now what we're going to do is see what happens when we use an invalid password. So as you may have noticed initially, we have the password Matson. But now over here in this try accept, we have a password Matson with a typo. So um, if our system is working as far as generating that hashed value in the super block, it should get mad at us, and it does. It accepts the authentication failure exception, so that is working. Now, one of the issues we're having right now um, is when we, after writing to the file, because as you saw earlier, robots are cool, and then here it's the encrypted version of that, um, we need to decrypt it. Um, for some reason, we're still diagnosing. Let me unlock the disk, or try to. Lorenzo's finger. It didn't encrypt it correctly. There's a few theories, like perhaps like we're doing something incorrectly with the encryption algorithm. Maybe it's a padding issue. For the sake of time, we haven't addressed it. However, we are confident that our implementation is pretty close to being really successful. Um, and yeah, uh, we some of the libraries we use to implement this are from the PyCrypto module. So we use crypto.cipher, crypto.util.padding. We employed bcrypt. Bcrypt is for making the password hashes. Um, if you want to get more into how exactly we do the hashing.
We decided that it would be really interesting to try to implement RAID 10. Um, so we chose to do RAID 10 because of its fast read and write speeds and its redundancy using mirroring for a backup disk. So I have a RAID demo that uh, basically goes through RAID 10 configurations, disk open test, disk close test, multiple disk open test, disk reading and writing test. I have also a recovery test, and then I have another file that tests the RAID with the um, TinyFS. So first, let's work with the disk. So here I have the code compiled. So the first thing is RAID 10 configuration. This is where the user inputs numpair and stripe size. The user is allowed to input any value into numpair stripe size, so they have the luxury of choosing whatever size they want, as long as it's numpair is greater than 2 and stripe size is 1 or greater, as as 2 and 1 are the minimum values for RAID 10, and the minimum amount of disk is 4. A limitation that um, that we have from this is that there's no control over the max amount of disk a user can make. So if they make enough disk, their system could crash due to not having enough capacity. For disk open test, as you can see here, we're making 4 disks, and we we have disk name TinyFS disk, and open disk returns a disk number, and yeah, here TinyFS disk has the extension of D1, D2, D3, D4. This is a naming convention we decided to use with RAID um, as a way to figure out what file is a RAID file and what file is a libdisk file by using this extension. It's also helps us virtualize the RAID disk as in TinyFS. It'll only see one disk, and under the hood there'll be multiple RAID disk. Um, Another way why the virtualization works is that we're inheriting libdisk. So um, libdisk and RAID will have the same functions, same parameters for open, close, read, write. And so in TinyDisk, it won't uh, choosing RAID and libdisk will not make that much of a big difference. So this is how we're able to virtualize the RAID disk and um, trick the TinyFS into thinking it's just one file named TinyFS disk, while in RAID we have the underscore D1, D2, D3, D4. Here we have a disk close test, and you can see here when we open we have a dictionary with 4 items, and then we're closed, it's cleared. So that works. And then we have multiple disk open tests. Here you can see that uh, this this disk number is opened and then closed, and you can see we're able to open it again right here, TinyFS disk, and then we're able to create uh, another disk open disk name 2, and you can see the TinyFS disk 2 is right over here too, and we can set them to different sizes. So that's working pretty nice. We have disk reading and writing test. This is where the striping and mirroring comes in. Um, and for writing, when you write to one disk, you're gonna have to write to the other disk that's part of the same pair. As in mirroring, you know, both disks of the same pair will have to be exactly the same. So if you write to one, you have to write to the other. And you can see here that we're able to write and read from a block, and we're able to do the same thing for the next block, showing that we could read and write data. And now my favorite part is the disk recovery test. Here you can see that um, we are deleting uh, TinyFS disk D1, and here it's missing, and then we're able to recover it using the it's redundant pair. So each pair, um, the way our recovery works is that it'll look at each pair, and for the damaged disk, it'll look for that healthy disk part of the same pair and copy that data over to the damaged disk to revive it. And you can see here in the data that we're able to get back the original data that was lost. So not only we get the file back, we get the insides of it back, which is really important, as that's one of the main reasons why there's RAID. So that's working that's focusing a lot more on the disk level. And now here's another script for TinyFS. The big thing about here is that we were having a lot of problems with overwriting. We have a problem in our open disk where it seems to be duplicating disk, and um, our, our super block and root inode blocks are being overwritten with data. Um, so that's a problem we couldn't fix. Um, but I believe the problem persists in open disk, or the function where we figure out the block's offset and disk number. But what this file is doing is you can see it's making a file system, mounting it, and then opening a new file. And we can show I can show you what happens. You can see we're getting data, so um, we are seeing data, and we are seeing it being mirrored, which is really great. But you can see that um, it's kind of overriding, like for example, block 0 is a super block and it's being overwritten. So that's a problem that we still have to deal with. But um, if I comment out the opening a new file, you will see the super block there. So that's how I figured out that it was just getting overwritten. Let's go all the way up. Let me try this again. If I scroll all the way up, you can see we have our magic number in the root inode. So it's there, it's just being overwritten, which is a problem somewhere in RAID that we just haven't figured out.